Ok. Allora, cominciamo questa cerimonia di premiazione della vincitrice del premio Anna Maria Cartacci 2023. Questo è un premio alla memoria della professoressa Cartacci, che è sponsorizzato e finanziato dal Dipartimento di Fisica e dalla sezione di Firenze dell'INFN. Qui abbiamo il vice direttore del Dipartimento di Fisica e il direttore della sezione NFN, Guido Risaliti e Giovanni Passaleva. Quindi quest'anno il premio è andato a Chiara Basile, che ha fatto una tesi sperimentale sullo studio della particella X3872 e io ho, insieme ai colleghi Carlo Civinini e Giacomo Graziani, abbiamo letto le tesi che erano state presentate per questo premio, erano state 23 tesi mi sembra, e la tesi di Chiara è risultata la vincitrice. Quindi io darei la parola a lei, siccome non siamo tutti italiani prima di tutto vorrei dare magari una parola al professor Straulino che conosce bene, ha conosciuto bene la professoressa Cartacci, magari vuole dire due parole.
Buongiorno a tutti, no, volevo dire soltanto che ho parlato con il figlio della professoressa Cartacci poco fa, che non ha ricevuto per un disguido la comunicazione, insomma, è andata persa e quindi avendola avvisato io stamattina, ricordando in realtà dell'avviso che era stato mandato, non ha fatto in tempo a venire. Volevo ringraziare tutti gli organizzatori del premio per la bella iniziativa, complimentarsi con la vincitrice e mandare un saluto a tutti, ecco, da parte del figlio della professoressa Cartacci.
Bene, dicevo, siccome non siamo tutti italiani, avremmo deciso di fare la presentazione in inglese, quindi a questo punto passiamo all'inglese e io do la parola a Chiara.
Can you hear me if I talk like this? Okay. Good afternoon, everybody. My name is Chiara Basile. First of all, I would like to thank you, Pier Giulio Lenzi, the entire Department of Physics, Florence, and everybody that made possible this very good opportunity for me. And today in this seminar, I would like to give you an overview about my thesis work, which is the study of this decay in which a B0 meson decays and produces such mysterious particle, which is the X3872, in association with a K0 short. This work was realized with the CMX experiment at LHC. And first of all, a little bit of history. The X3872 was discovered by the Bell experiment in 2003. And this resonance was first observed in the decay channel of a B+, which produced the X, and a K+. Then the X is observed as a bump in the invariant mass of the J psi and 2 pions. So the presence of the J psi as its final state suggested at the beginning that this mysterious new particle could be, for example, an excited level of the charmonium. What is a charmonium? It's a bound state of a C quark and anti-C quark. And it's described with a potential which is very similar to the hydrogen atom potential. So the excited state and their dynamics, their characteristics, and their energies especially are very well predictable. And as you can see, they follow a nomenclature which is quite similar to the one of the hydrogen atom. But unfortunately, during, or maybe luckily, between the 2005 and 2020, the discoveries and the observation made around this new discovered particle, were mostly in conflict with what was expected for a harmonium state. The most important one is the measurement of the X quantum number to be JPC 1++ by LHCb, an experiment which is at LHC. And this quantum number conflicts with the harmonium state of the mass of the X3872. So what we understand out of this is that the conventional quark model, which just predicts quark aggregation made by 3 quarks, the baryons, or 2 quarks, mesons, is not enough to explain and to describe the various states that we observe in nature, and it must be extended. So the extensions of the conventional quark models varies a lot, and there are 2 hypotheses on the X3872 internal structure, which place themselves at the very opposite, at 2 very opposite extrema. The tetraquark hypothesis that predicts for the X a compact structure made by 4 quarks, which are strongly kept together by the strong forces. And on the opposite, we have instead some models that want the X to be a sort of molecule made by mesons, 2 mesons, the D0 and D0 bar star. This is strongly motivated by the fact that the X3872 mass is measured to be slightly below the direct sum of the 2 meson mass, so accounting for a very small binding energy. Well, now we don't have a conclusive response on what is the actual internal structure of the X3872, and more investigation has to be done. This is the state of the art that we have by now. On the x-axis of this plot, I show you the branching ratio of production of the X in various B decay channels, with the X that decays into a J psi and 2 pios, as I showed you before. Something that you can directly observe, and then it seems that the X has a quite double probability to get produced by a charged B decay with respect by a neutral B decay. Okay, this is something that can easily fit in the simple stator quark formation theory, because that one predicts that the production channel from charged B receive a contribution from 2 diagrams, while the production channel from a neutral B receive contribution by just 1 diagram. So this gives us a hint. Using and measuring with a very high precision the branching ratio of the production of such mysterious particle in B meson decays may provide a handle to probe the internal structure of this particle. Indeed, as you can also observe, these error bars over here are quite large, so any conclusive response cannot be provided. But the effort now is to measure with good precision this quantity, and my analysis actually aims to provide the first measurement at LHC of the branching ratio of the process in which the X is produced by a B0 and with a K0 short in the final state. The strategy that we use is to measure this ratio R, which namely, as its definition is the ratio between the branching ratio of interest, and so the one with the signal channel, and the branching ratio of the normalization channel, which is the same as the signal channel. The only difference is that a psi to S is produced in place of the X3872. The psi to S is the first excited level of a harmonium. Experimentally, this quantity is very convenient because it receives contribution just by the number of reconstructed events in the signal channel, the number of reconstructed events in the normalization channel, and their selection efficiency on these two. And at the same time, you have many cancellation of some constant quantity. For example, here there is the cross-section of production of BB bar pairs inside the CMS detector, the luminosity of LHC itself. And in particular, in this ratio, many systematics related to the reconstructions of the two channels cancel out because the X and the Psi2S have a mass difference, which is of only 185 MeV. So they have quite the same phase space available. This measurement was never before performed before at LHC, but it was performed at Babar in 2008 and at the Bell experiment 2011. As a reference, I will take in my work the Babar measurement, and the goal is to improve the precision on these measurements. So the experiment that was used for this analysis is the CMX experiment, which is an experiment of the Large Hadron Collider, LHC, which produces proton-proton collision at a center of mass energy of 13 TeV. And CMS is a compact but very large detector, which is CMS stands for compact muon solenoid, and it is made by many subdetectors: a tracker inside, an electromagnetic calorimeter for the detection of electrons and photons, an hadronic calorimeters for the detections of hadrons, so pions, counts, but it's not able to perform particle identification on that. A huge solenoid, which is able to produce an internal magnetic field of 3.8 Tesla, which is an enormous value. And outside the solenoid, we have the muon system for a very precise detection of muons. Well, how does our signal look like? It should look like this, ideally. Like you have the collision of proton, B0, either a B0 bar is produced, it flies for a certain distance, then after a while it decays and produces a K0 and our beloved particle, the X3872. Well, the K0 produces these two oppositely charged pions. The X3872 is observed in a final state in two muons that are the decay product of the J-psi and two oppositely charged pions, which resonate into a Rho resonance. So from the point of view of the CMS detector, we only can see the pions, the muons, and again the pions. So 4 muons and 2 muons and 4 tracks inside the detector. The muons, the muons would look like this. So a track that leaves a signal inside the tracker and then in the muon system. And the tracks instead would look like this, like some signals inside the tracker because they are charged, and then leave the energy deposit inside the hadronic calorimeter. But actually, usual CMS events look more like this, where it's very difficult to pick up the 4 tracks that we need and the 2 muons that we need to reconstruct the signal we are looking for. And that's why the high energy physics experiment and of course also CMS has to put in place several steps, several strategies to select the interesting event and to extract the signal of interesting. The first step is the online selection, the CMS trigger. Inside the LHC ring, the collision of 2 proton bunches happens every 25 nanoseconds. So the rate is 40 megahertz. And keeping all the events, all the rates of events would be, first of all, impossible. And Secondly, also unnecessary, because only in a really tiny fraction of those events some interesting physics processes happen. And that's why we have a trigger system, which is made by several levels. The first level is the level 1, is hardware based, and it like perform a decision on whether to keep or to reject the event, basing on very fast quantity that it gets promptly from the detector. If the events seems like to be quite interesting, then it is forwarded to the high level trigger, which is a software basically. And but it is a little bit slower because it works with some more refined quantities. It tries to match tracks and maybe muon deposit into the muon chamber to reconstruct the higher level object. And at the end of the selection procedure, the rate of events that we save on the disks on the data center at CERN is only 1 kilohertz. And if you compare to the 40 megahertz of the beginning, then you see that only a really tiny fraction of these events had something interesting inside. For this analysis, we use a trigger that requires the presence of 2 muons that are compatible with a J-psi resonance in terms of invariant pass, and an additional track that should come from the same point where the muon were produced. So basically, these 3 objects could fire up the trigger. Now, a little disclaimer that has to be made before going on. What you will see from now on is just content of my master thesis, and it's not yet approved by the CMS collaboration, so it's a private work. And so coming back to physics, one could think that, okay, the trigger provides us all the events that potentially have something interesting for us. But now, inside each event, there are many tracks, many muons in principle. So what we have to do is to be careful in trying to, in picking, for example, 2 muons and 2 tracks to combine them and try to extract the X3872 peak. Because if we, like, without any selection, take all the possible combination of 2 muons and 2 tracks inside the events, what we get in the Monte Carlo simulation is a situation like this, in which this one in purple is the combinatorial background, which means basically you pick up random combination of objects which are not actually your signal. And the blue, very shy peak over here is the signal itself. So our goal now is to make it stand out and remove all this combinatorial background. And to do this, we need to work a little bit more, which means to put in place more refined selections, which make use of the topology of the events inside the detector. For example, I will not be too technical in this, but if you want, we can discuss further later. Basically, what you want is just to select K0 tracks that are very well compatible with a K0 short hypothesis in terms of mass and in terms of where they come from inside the detector, right? And the same you do to reconstruct the J-psi and to pick only the 2 muons that are very likely coming from the same point inside the detector. This is an information that you can use. And in the end, what you want to do is to reconstruct this object over here, the B0. And why B physics is so important in CMS, but also LHC in general? Because this particle is very useful because it has a time life which is large enough and allow the particle to fly a little bit inside the detector, but just enough for the tracker to recognize that that particle didn't decay at the very center of the PP collision. Okay, so what you will see is that the final state object will arise from a point which is a little bit detached with respect to where the proton touched in the very first moment. And so also to reconstruct this object, you will combine together the K0 element, the K0 object that you reconstructed, the two muons that are likely to come from a J-side decay, and two tracks, and using a fit to a common point, you can really boost on one side the resolution on the B resonance, but on the other side now, our peak that we are looking for before stand out, and the combinatorial background is very well rejected by using this procedure. But it is not enough yet. Now we have to define a strategy to decide whether a B candidate is signal or background. And to do that, we train a machine learning algorithm, a Boolean decision tree, which has to be trained with a very pure signal sample, which is the Monte Carlo simulation itself of the process, and also a very inclusive background sample, which is extracted by the data themselves. In the data, we apply the same reconstruction that I just showed you, trying to look for a B candidate, and each reconstructed mass could be places is in a wide range, but we know that the B peak should be placed in a very well-known value, and so we pick only the data that places on the sides, on the side bands of this peak, because we are pretty much confident that those events are just background, are just combinatorial background in the data, right? So they resemble what we want to reject. And so we feed the BDT with these two alternative samples, and we pick the feature, the kinematic of feature that seems to us to be better discriminating between signal and background. For example, this distance between the primary vertex and the secondary vertex is very much impacting on the response of the BDT in the end. So, and the response of the BDT look like this, a continuous variable between -1 and 1, and which is able to separate what is background and what is signal. Then we combine this quantity with another one, the reconstructed invariant mass of the two pions, which are coming from the X3872 candidate. Because as you can see in background sample and in signal sample, they have a pretty different distribution. And we build a 2D plane with these two variables where we optimize a cut. So we isolate the signal in this little tiny region over here. This one is dominated by background, but here the signal clusterized. So now this defines completely the analysis workflow, and we can apply it to the data, to the Monte Carlo, and see what it comes out. The channel to which we apply it is the normalization channel, the one used in the ratio that I mentioned at the beginning, and where upside to S is produced instead of X3872. We apply the same selection because this is crucial to allow the systematic cancellations inside the ratio. But the little tiny difference is that the psi to S has a narrower phase space available because its mass is smaller with respect to the X3872 mass. Nevertheless, and this can be visible here, but nevertheless, the BDT response on the Monte Carlo of the channel with the psi and the channel with the X seems to be not very much affected by this difference in kinematics. So we decided to keep the BDT weights as they were by training on the X sample, and we shifted the cut on the invariant mass of the two pions a little bit to match the signal region for the normalization channel. And so if we apply this combined cut on the PDT and on the invariant mass of the 2 then we get a situation like this in which the background was rejected by almost 90% and signal efficiency is kept at 34%. And also, if we restrict ourselves in this region here, where it is a narrow region where the signal is expected, and we look to the psi2s mass in the signal region, then we observe that we have a pretty good agreement between data and Monte Carlo. So the data resembled very much what we expected from the beginning, which is a very good check in the end, because it states that our analysis strategy is effective, is going in the right direction. And also on the side of the normalization channel, we have all the ingredients to perform the complete measurement of its branching ratio, because we only need the number of reconstructed events in the normalization channel, which is basically the integral of the peak in the narrow region below, in the signal region, so a narrow region below the peak, and the selection efficiency that we estimate from the Monte Carlo, and some quantities which are constants, for example, the cross-section production of BB bar pairs in CMS, the branching ratio for the J-psi into 2 muons, and the luminosity of CMS in RAN 2. Well, so the results that we obtained is comparable with the world average, which confirms again then the results, the strategy is going in the right direction. And on the signal channel, unfortunately, we cannot perform the same, because it follows the blind analysis approach, which means that we hide ourselves the data in the signal region. We cannot look at them, because otherwise we will be like influenced by the signal that we see over there. In this case, we know that there is a peak here, but we would influence it by the yield of event in that region. So the only thing that we can do is to provide the estimation in this case, which means to generate a pseudo dataset using the model of the background fit and the model the model, yes, of the signal fit to the Monte Carlo. In this case, we use the data of the sidebands. In this case, we use the Monte Carlo, and by fitting the whole the whole spectrum of the pseudo dataset, we can provide an estimation of the yield in the case of the signal channel. And so our strategy is complete. We can provide a final estimation of the ratio R by using the estimated number of events reconstructed in the signal channel, and the measured, in this case, this is a measure of number of events in the normalization channel, and the selection efficiency that I mentioned you before. And look, they are similar. They are ordered to the 10 to the minus 5 in both cases. This is the ratio R that we obtain, which leads to an estimation of the branching ratio of the production of dx by the B0 decay, which is 1.70 times 10 to the minus 6, compatible with the Babar measurement of 2008. Well, this was expected, because as I told you, I injected the measurement of Babar inside this procedure to normalize the Monte Carlo. Okay, but this is a check that has to be done, because in the end it proves that our analysis didn't introduce any bias inside the procedure. So also you see we have only estimation for statistical uncertainties, and studies on systematic will be done in the future. They are in process. And so to conclude, what this work would like to go through is the research of a counterpart, experimental counterpart to feed the QCD models that wants to find a way to represent and provide a satisfactory description of the internal structure of the X3872. My works proved to be very effective on the measurement of the normalization channel, because the branch duration that we obtained agree with the world average. And this measurement would be the first one at LHC to measure the production of the X by the B0 decay in association with a K0 short. And also, since Run 3 at LHC started the last July 2022, then we can perform the same analysis with the upcoming Run 3 data. And moreover, they designed a more effective trigger that is able to be much more, help me to say much, sensible to this kind of processes, and so to boost the sensitivity and to make this measurement very competitive, also with respect, for example, Bell, LHCb, and PAPAR. And so this concludes my seminar, and I thank you all for the attention.